Hi, in this video I'm going to guide you step by step on how to use the I4I Hydrogen Damage Screening Tool for the API 579 Part 7. The link to the tool is in the video description, and this video is meant to be used together with the tool. The API 579 Part 7 exists because hydrogen damage can silently weaken carbon steel equipment in sour service. You can have blisters, hydrogen-induced cracking, or stress-oriented hydrogen-induced cracking inside the plate, and from the outside, the equipment may look normal until you suddenly have a leak or a rupture. The API 579 Part 7 helps you screen whether your condition needs a formal fitness for service evaluation and what level of evaluation is appropriate, so you don't guess when hydrogen damage is involved. Before we start, let's make three terms very simple. Hydrogen blistering is when hydrogen forms internal cavities that create a bulge like a bubble under the steel surface. Hydrogen-induced cracking is when hydrogen creates planar cracking inside the plate, usually parallel to the surface, often in step-like arrays. Stress-oriented hydrogen-induced cracking is the more dangerous one near welds and high-stress areas where cracking is oriented by stress and can behave like a crack-like flaw that needs a higher rigor approach. Now here is how to use the screening tool. You will answer every question in the Part 7 tool by selecting Yes, No, or NA. Use NA only when the question truly does not apply to your equipment or your objective. For example, some questions are specific to hydrogen-induced cracking spacing requirements, and if you only have isolated blisters with no hydrogen-induced cracking, then NA makes sense there. But do not use NA just because you are unsure. If you are unsure, treat that as a signal you need better inspection information before you can defend a screening decision. After you answer all questions, click the button that says Check if FFS is needed. The tool will summarize whether you have triggers that require a formal Part 7 evaluation, whether Level 1 or Level 2 is applicable, or whether the case is driving you to Level 3 and potentially a crack-like flaw assessment. Now let's go question by question with detailed refinery scenarios so the logic is very clear. Question 1 asks if inspection identified hydrogen blistering, hydrogen-induced cracking, and/or stress-oriented hydrogen-induced cracking in the pressure boundary. A realistic refinery scenario is a sour water stripper, overhead accumulator, or sour water drum where straight beam UT mapping finds laminar blister-type reflectors, or a wet hydrogen sulfide service drum where UT shows step-like planar arrays consistent with hydrogen-induced cracking. Another common example is an amine regenerator reflux drum or a sour gas knockout drum where hydrogen charging conditions exist and you start to see laminar indications during an outage scan. If any of those hydrogen damage signatures are present, select Yes. Question 2 asks if the damage type is clearly distinguished as blistering, hydrogen-induced cracking, and/or stress-oriented hydrogen-induced cracking instead of being reported as generic lamination. In a refinery, this matters because lamination might be old plate lamination or it might be hydrogen damage, and the assessment path is not the same. A good example is when the inspection report specifically describes a bulged blister cavity versus describing planar, stepwise reflectors at multiple depths that fit hydrogen-induced cracking, or describing an oriented crack-like network near a weld heat-affected zone that fits stress-oriented hydrogen-induced cracking. If your report is not distinguishing what it is, select No, because you cannot defend a Part 7 path without knowing what damage type you're really dealing with. Question 3 asks if there is evidence the indication is crack-like rather than only a contained laminar reflector. A refinery example is a sour water stripper drum seam weld area where MT or PT finds a surface breaking linear indication, or angle beam UT suggests a crack-like feature near the weld consistent with stress-oriented hydrogen-induced cracking. If the feature is crack-like, select yes here because that is a limitation for simple screening and it pushes you toward level 3 and possibly part 9 style crack-like evaluation. Question 4 asks if the component class is understood well enough to decide which assessment levels apply, such as type A versus type B components. A refinery scenario is a straight shell course on a vertical drum, which is usually treated like a type A shell under internal pressure, versus a nozzle region on a hydrotreater cold separator, where local discontinuity stresses are more significant and the component is not treated the same way. If you cannot confidently classify the component region, select no because the assessment level decision depends on that classification. Question 5 asks if you are trying to use level 1 or level 2 for stress-oriented hydrogen-induced cracking. In practice, stress-oriented hydrogen-induced cracking near welds is the case where you do not want to treat it like a simple metal loss issue. A realistic refinery example is a wet hydrogen sulfide service vessel where stress-oriented hydrogen-induced cracking is reported in the weld heat affected zone of a longitudinal seam. If the damage is stress-oriented hydrogen-induced cracking and you were hoping to stay in level 1 or level 2, that is a trigger to move up in rigor. So if stress-oriented hydrogen-induced cracking is involved, select yes here because it tells the tool you're not in the simple screening territory. Question 6 asks if the damage is close to a weld seam or major structural discontinuity like a nozzle, attachment, or geometry change. A classic refinery case is hydrogen-induced cracking found near a nozzle reinforcement pad on a sour gas scrubber, or blistering located near a longitudinal seam weld on a sour water drum shell course. The reason this matters is that welds and discontinuities have higher stress and can change the risk profile. If the damage is close to a weld or a major discontinuity, select yes, because that typically drives you to a higher level evaluation. Question 7 asks if the component contains a multitude of closely spaced blisters where interaction matters. A refinery example is a band of blisters around a sour water drum or a wet hydrogen sulfide separator where multiple blisters are packed closely together. When blisters are clustered, you can't always treat them as isolated. If you have a dense cluster, select yes, because combining an interaction logic becomes important and can trigger level 3. Question 8 asks if your objective is to establish the reduced maximum allowable working pressure of the damaged component and/or the reduced maximum fill height of the damaged tank at a coincident temperature for continued operation. A refinery scenario is when an operations team wants to keep a sour water stripper drum running until the next turnaround, but integrity needs a reduced allowable pressure, or a tank case where a reduced maximum fill height is needed to manage stress at the damaged region. If your decision is about continued operation limits, select yes because that means you are using Part 7 to support a re-rating decision, which typically requires formal evaluation. Question 9 asks if you have an inspection sketch or map showing locations of each blister, hydrogen-induced cracking, or stress-oriented hydrogen-induced cracking, and which plate or zone is affected. A refinery example is a map of a sour water drum shell course where you mark clock position and elevation, label each hydrogen-induced cracking zone with an ID, and tie those IDs to UT screenshots or scan files. If you don't have a map like that, select no, because the assessment depends on defensible location and sizing. Question 10 asks, for hydrogen-induced cracking, whether the required spacing measurements are captured, including edge-to-edge spacing to the nearest hydrogen-induced cracking or blister and longitudinal spacing. A refinery example is a wet hydrogen sulfide knockout drum where multiple hydrogen-induced cracking zones exist, and you document spacing both circumferentially and longitudinally. If spacing is not measured, select No, because spacing affects whether you treat features as interacting or separate. Question 11 asks for hydrogen-induced cracking, whether spacing to the nearest weld joint is documented. A common refinery scenario is hydrogen-induced cracking detected near a longitudinal seam on a sour water stripper overhead drum. You need the shortest distance from the hydrogen-induced cracking edge to the weld because near weld conditions change the evaluation path. If you don't have that weld spacing, select No. The question 12 asks for hydrogen-induced cracking, whether spacing to the nearest major structural discontinuity is documented, such as a nozzle. A refinery scenario is a sour gas scrubber shell where hydrogen-induced cracking is found near a large inlet nozzle reinforcement. If you don't have spacing to that nozzle or attachment, select No, because discontinuity proximity can drive higher level analysis. Question 13 asks for hydrogen-induced cracking, whether through thickness extent is defined and whether you can report remaining undamaged ligament to both surfaces when subsurface. A refinery example is UT sizing on a sour water drum that shows hydrogen-induced cracking reflectors at a certain depth range, and you document the remaining ligament to ID and OD. If you don't have that depth characterization and ligament information, select No. The question 14 asks whether hydrogen-induced cracking is classified as subsurface versus surface breaking. A refinery case is when UT suggests the hydrogen-induced cracking array connects to the ID surface, or when surface examination indicates breakthrough. Surface breaking behavior is a major trigger because it behaves more like a crack-like flaw. If you can't classify subsurface versus surface breaking, select No. The question 15 asks for stress-oriented hydrogen-induced cracking, whether spacing measurements are captured and crack-like dimensions are defined. A refinery scenario is stress-oriented hydrogen-induced cracking near a seam weld in a sour water stripper drum where you size it as a crack-like feature with length and depth, and you also document distances to nearby damage and discontinuities. If stress-oriented hydrogen-induced cracking exists, but you don't have crack-like sizing, select No, because you cannot defend the next steps. Question 16 asks for blisters, whether blister size is recorded in the form needed for the intended level. A refinery scenario is blistering in a sour water drum shell plate where you record maximum blister diameter for screening and also record longitudinal and circumferential axes if you might need a higher level method. If you don't have those dimensions, select No. The question 17 asks whether blister spacing to the nearest blister or hydrogen-induced cracking is documented, and whether you considered whether neighboring blisters must be combined. A refinery example is two blisters close together on a wet hydrogen sulfide separator shell course. You have to decide whether to treat them as interacting. If you don't have spacing data, select No. The question 18 asks whether bulge direction and projection above the surface are recorded. A refinery example is an OD bulge on a sour water drum, where you measure the projection with a straight edge and record whether the cavity is internal or external. If you don't have bulge and projection recorded, select No. The question 19 asks whether minimum remaining wall thickness to the blister cavity is determined, meaning the remaining ligament from the opposite surface. In a refinery case, for an internal blister, you need the ligament from OD to cavity, and for an external blister, you need the ligament from ID to cavity. If ligament is unknown, select No because ligament controls strength. Question 20 asks whether you checked and documented periphery cracking and whether it extends in plane and or through thickness. A refinery example is blistering near a weld in a sour water stripper drum where periphery cracks can form around the blister boundary. If you did not check for periphery cracking, select No. The question 21 asks whether you checked for crown cracking and or existing vent holes and recorded dimensions if present. A refinery example is a blister on a sour gas scrubber plate that has a small vent opening or a crack at the crown. Those features can change the failure mode from bulge to leakage or crack propagation. If you didn't document crown cracks or vents, select No. The question 22 asks whether spacing to the nearest weld joint and nearest major discontinuity is measured for blisters and shown on the sketch. A refinery scenario is blistering close to a longitudinal seam weld on a sour water drum or near a nozzle. If you do not have those distances, select No. The question 23 asks whether thickness data is available to define undamaged thickness away from the damage area and the minimum measured thickness at the damage. A refinery example is a UT grid on a sour water drum where you establish a representative remote thickness and then define the minimum ligament at the damage. Without that remote thickness and local minimum, you can't defend remaining strength calculations. Question 24 asks if appropriate NDE methods were used for the damage type. A refinery example is using straight beam UT for sizing blisters and subsurface hydrogen-induced cracking, and using angle beam UT and surface exams when crack-like stress-oriented hydrogen-induced cracking or surface breaking behavior is possible. If the inspection method was not appropriate for the damage type, select No. The question 25 asks for subsurface hydrogen-induced cracking, whether you avoided relying on methods that cannot define subsurface hydrogen-induced cracking, and whether you have volumetric characterization like UT mapping. A refinery example is someone saying RT looked clean on a sour water drum, but that does not replace UT mapping for subsurface hydrogen-induced cracking characterization. If you don't have UT or equivalent volumetric data, select No. The question 26 asks whether the equipment remains in hydrogen charging service with no effective halt, such as barrier coating or process change. A refinery scenario is a sour water stripper drum that continues in wet hydrogen sulfide and hydrogen charging conditions, with no barrier coating or overlay installed. If hydrogen charging continues, select Yes because progression remains credible and higher rigor decisions and monitoring are typically required. Question 27 asks if any hydrogen-induced cracking is classified as surface breaking. A refinery example is UT and surface exam indicating breakthrough to the ID surface in a sour water drum shell. If surface breaking is present, select Yes because it triggers crack-like considerations. Question 28 asks whether through-wall extent of hydrogen-induced cracking appears significant enough that a fracture assessment may be required rather than only local metal loss equivalency. A refinery case is a deep hydrogen-induced cracking array where remaining ligament is small and you suspect crack-like behavior could control, especially under operating pressure and local stresses. If the depth extent is significant, select Yes, because that's a trigger toward fracture-based evaluation. The question 29 asks if, when a crack-like assessment is needed, you are prepared to evaluate hydrogen-induced cracking or stress-oriented hydrogen-induced cracking as a crack-like flaw using the appropriate pathway when directed. A refinery example is sizing a hydrogen-induced cracking array as an equivalent crack length in the evaluated direction and using the maximum through thickness extent as the crack depth. If you cannot define those crack-like dimensions, select No because you cannot proceed defensively. The question 30 asks if you have a basis for remaining life planning, such as evidence damage is stable or progressing at a known rate, or you can set monitoring intervals accordingly. A refinery example is comparing UT mapping results across 2 turnarounds on a sour water drum and seeing the hydrogen-induced cracking zone size is stable, or setting a defined monitoring interval if you believe it is progressing. If you don't have stability evidence or a monitoring plan, select No. The question 31 asks if there is a plan to eliminate or control hydrogen charging, such as coating, overlay, process changes, or inhibitors. A refinery example is planning a weld overlay or barrier coating on a sour water drum during turnaround, or making chemistry control changes to reduce charging severity. If you have no mitigation plan and charging continues, select No because risk management becomes harder. Question 32 asks if blister venting is being considered, whether venting prerequisites and safety constraints are addressed. A refinery example is considering venting a blister on a sour water drum, where you must confirm blister orientation, confirm it's not already vented by cracks, ensure you are not in a prohibited service condition for that approach, and plan safe drilling and purging controls. If venting is being considered but prerequisites are not addressed, select No. The question 33 asks if repair is being considered, whether there is awareness hydrogen-charged steel may require controls and re-examination after repair. A refinery example is planning weld repair in a wet hydrogen sulfide service vessel where you consider hydrogen bakeout and then require MT or PT recheck after repair. If you are planning repair but not planning those controls and re-exams, select No. The question 34 asks whether there is a defined in-service monitoring approach when hydrogen charging persists or damage is near welds or discontinuities. A refinery example is setting periodic UT mapping on the sour water stripper drum shell plus angle beam UT near seam welds for stress-oriented hydrogen-induced cracking monitoring and adjusting intervals based on severity and progression. If you don't have a defined monitoring approach, select No. The question 35 asks if you are prepared to document the assessment inputs and decisions in a structured way, including measurements and sketches. A refinery scenario is maintaining a formal table of damage features with IDs, dimensions, spacing, ligaments, cracking observations, and tying it to an annotated shell map. If documentation is not structured and traceable, select No because the value of Part 7 depends on defensible records. Now let's talk about what the final result means. If the tool indicates that the API 579 Part 7 fitness for service evaluation is likely needed, it means your answers triggered conditions like proximity to welds and discontinuities, crack-like behavior, stress-oriented hydrogen-induced cracking presence, data gaps, or service conditions where damage could progress. That is not a failure. It simply means you should not rely on screening assumptions. You should gather the correct sizing data, select the correct assessment level, and, when required, treat the condition as crack-like and use the appropriate higher rigor pathway. If the tool indicates a formal Part 7 evaluation may not be required, it means based on your current inputs you did not trigger those escalation conditions, but it does not mean the equipment is safe forever. If service severity changes, if hydrogen charging continues, if new indications appear, if you change operating conditions, or if inspections show growth, you should rerun the screening. Let me close with the most important takeaway. Hydrogen damage is one of the easiest mechanisms to underestimate because much of it is subsurface and can evolve near welds and discontinuities where stress is higher. This tool forces you to classify the damage correctly, confirm the right inspection measurements are available, and recognize when you must step up to level 3 and crack-like evaluation. Used correctly, it becomes a practical gate that helps you avoid guessing and helps you build a defendable path to safe operation.